think we are good to go. So, hello, welcome you all to the 10th session for 10th problem solving session for the course titled Multirate Digital Signal Processing. Myself, Saurashis Chatterjee, a PhD scholar from IIT Kanpur, and today I am going to solve a few problems based on the content of 10th week lectures. So before diving into problems, let us just briefly uh, revisit whatever being taught at 10th week. It's basically in continuation to 9th week lecture itself. Mostly see the orthogonality of OFDM, multi-carrier transmission, you can also say, and various ways to introduce redundancy. Redundancy is, basically introduced to combat different kind of interference, which I will come later also. It's basically the goal is to ensure a robust or reliable communication. So among redundancy, two of the concepts we have seen in lectures are zero padding and cyclic prefix. Now in context of why these are necessary, we have also seen the intra and inter block interference. Intra-block interference means symbols within a block interfering with each other, whereas inter-block interference refers to when symbols from different blocks, like one blocks overlaps with another or create interference to other. These both are also together known as multi-carrier modulation impairments. And basically to combat these impairments, or to reduce their effect, or ideally to alleviate them or mitigating them completely, this redundancy has been used in data in form of zero padding or cyclic prefix. Another kind of very important concept we have seen a kind of matrix structure known as pseudo-circulant matrix. Although this has been extensively analyzed in the lectures, we'll solve few problems based on this structure of this matrix, and we will see in details again. It's worth of revisiting, because the structure of pseudo-circulant matrix and Toeplitz pop property or the circulant property or why we are calling it pseudo-circulant, not circulant. These kind of things are very important for intuitive understanding of what's going on underlying. So keeping them in mind, let us move to our first question. So first question is about a block transceiver when m is equal to 10 and a channel transfer function Cz, which is given as follows. By the way, when you say that block transceiver with m is equal to 10, you can remember from the previous lectures and also from our problem solving session, we have seen basically m is equal to 10 block transceiver means there are m filters on transmit and receiver side both. On transmitting side we call them transmit filters and receive side we call them receive filters. Also in Multirate-DSP framework, if we derive the concepts from there, the filters on transmit side are also known as synthesized filter, because their goal is to combine m parallel signals before transmission, whereas on the receiver side you call the receive filters as uh, analyzing filters. Why? Because you have received a particular signal and you send it to different filters to analyze its behavior on different spectrum. So when we say that just a minute, when you say block transceiver with m is equal to 10, this is nothing but for your visualization purpose. It's like on transmitting side you have 10 filters Of course, there are other blocks also, like delay or advance. I am just ignoring them as of now for just. So m is equal to 10. So although this is not very relevant to the question here, this is just to help you visualize the block transceiver with m is equal to 10. These filters we call as synthesis filter. This we call as analysis filter. Okay, so therefore let's get back to question. U is equal, you have m is equal to 10, therefore the question you have n input signals that you fed to this block transceiver, and your channel transfer function is given as follows: channel transfer function, sorry, channel transfer function cz is given as 1 plus 2 z inverse minus z to the power minus 2 plus 0.8 z to the power minus 3 plus z to the power minus 4. So writing this channel transfer function, or this problem is pretty much generous, that we got channel transfer function in this format, z transform, because it is very easy to get the time domain representation of channel or the channel taps in a very easy way. You just need to pick the coefficients and they become the channel taps. So because cz is nothing but, I am following the notation in the lecture where I runs from 0 to infinite, corresponding taps which we denote as not capital C, let us denote them with small ci, otherwise it will be misleading. Ci z to the power minus I, correct, where ci's are channel taps, correct. So you get c0, again writing that capital should be small. Okay, if you see the expression of cz, you can see c0 correspond to the constant element because it have z to the power 0. c0 is 1, c1 is 2, c3 is minus 1, c4 is 0.8, and c5 is 1. So you can see there are 5 channel, just a minute, I think there is some problem in right here, the system is slowing down somehow. Okay, I'm just turning my video off for a smooth writing experience here. I hope this will help. says my mic is not working, but it should not be the case. Asking me to reload the I think things are better now. I just hope so. Okay. Okay. I think the situation is better now. Okay, let us start from where we left. Sorry for the inconvenience caused. Some issues. Slow down in system. So where are we? Okay. So we have seen this particular channel have 5 channel taps. So we have seen from earlier lectures and from our earlier previous session also, if there are 5 channel taps, then this corresponds to this corresponds to 5 minus 1 is equal to 4 symbols of ISI, inter-symbol interference. Therefore, to eliminate inter-block interference, as mentioned in lecture, we need 4 0 padded samples. And we are making use of this expression that number of 0 to be added is equal to number of channel taps minus 1. Since we have number of channel taps 5 minus 1, therefore 4. So the length of 0 padding to eliminate interblock interference is 4. Therefore the first option is the correct one. With that, let us move to our second question. So this is also a question quite directly from lecture, that we have already seen the transfer function of multi-carrier system is Tz can be written in this format: Sz, Cpcz and Gz. So it asks what are the properties of Cpz. So if I am answered directly from lecture, we have seen that Tz is nothing but a matrix which is created by a polynomial. I mean, its elements of the matrix are polynomial, and this Cpcz, where this subscript Pc refers to pseudo-circulant, is a pseudo-circulant matrix which all satisfies Toeplitz property. Remember the option, you can be very tempted to take for circulant one also, like it's Toeplitz, we know that from lecture. Of course it's not symmetric, and we'll see later when you analyze the structure of Cz in detail. But remember, it's a pseudo-circulant, so it's not circulant. If you take the circulant also, then your answer is going to be wrong, because it's pseudo-circulant because its structure is closely follows the circulant structure, but technically it is not circulant, so that is why it's called pseudo-circulant. So let us analyze the structure of this CPCZ. It's a square matrix, of course, and its structure is as follows. It is constructed basically in a particular way, so I'll mention that. Let me write down the first column, C0z, C1z, dot 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 up to Cn minus 1z. So this is the first column. Okay, what happens in the next column? These elements shifted downward by 1 unit when you move to first to second column. It's also another way to saying that the elements of a column, okay, let me write it down, it's better. Like C0z you have seen in the first row, in the next column, that is second column, your C0z comes here, and it maintains the sequence, by the way. So up to you come here, Cn minus 2z. Now it shows a circular behavior. Why? Because the last element is, you kind of visualize it, kind of pops out and goes back here. So Cn minus 1z appears here. It doesn't go out of matrix, or you don't eliminate it. It just kind of, you can consider when you see from the first column, it just moves out and enters here. So it's like this in a circular fashion. And by the way, why it's called pseudo-circulant, will come into that minute. We have a delay term z inverse multiplied here. Similarly, third column, C0z brings down all the elements, comes down 1 unit when you move to one column to the next. So C0z is here, C1z here, we have Cn minus 3z here, this one comes down here, z inverse Cn minus 1z, and this one goes here and multiplied with z inverse Cn minus 2z. It is n minus 3 anyway. C n minus 3 z, and this goes on. The last column, let us write down because it helps to visualize things. This C naught z comes here, C naught z comes here, and just a minute. C naught z comes here, therefore C1z you know that should be here, of course multiplied by z inverse. Sequence however is being followed as it is. Similarly here you will have z inverse C n minus 1 z. So this is the structure of this pseudo-circulant matrix. So first let us see why it is called pseudo-circulant. So for that we need to know what is the structure of circulant matrix. So let us give you a small example of circulant matrix here. If M is a circulant, first I will draw the structure first and then I will give the technical definition of it. In that way it really helps, because if I first give the definition it becomes difficult to visualize it. So let us first see what its structure is really, and then from we can infer the definition ourselves. Of course technical different, not exactly in a technical way, but we can understand what's happening. So M is a circulant matrix. M has following structures. It's M0, M1 up to M n minus 1. We are also considering to be a n cross n matrix only. Next time it will come, M0 will step down 1 unit, M n minus 1 circle back here, M1 will be here, and you will have M n minus 2 here. Similarly at the end we will have M0 here, we will have M1 here, M2 here, like that. So what are the things you are seeing here? If you see column wise from one column to another, what is happening? As if the elements are rotated back by 1 unit downwards. Downwards in sense, rotated in sense, the last element of a column pops out, at least it appears, and then goes back to the initial position of that column, and rest of the columns just shift downwards by 1 unit when you move to one to next column. And another way of seeing that, if you see the rows, if you see the columns and rows have same elements only. If you see row wise also, you see column wise first, M0, M1 up to Mn minus 1, this also consists of same elements, just in a different order, slightly different orders. This one same for it. If you see row wise what's happening, if you move to one row to another, if you see the elements are shifted right by 1 unit, that every elements of the row is shifted 1 unit, or one step right compared to its preceding row, correct? So we can infer the definition from this, like it. Let me write it down. So a circulant matrix is a square matrix where each row and each column consists of same elements and each also a nice way to see that instead of seeing that elements are shifted by rotated by 1 unit right, the entire row is being shifted on a right. You can visualize from that perspective also. So whatever we, yeah, and each row is shifted 1 unit right compared to its previous row. Correct? So when you compare this with this is a circulant matrix. This is a circulant matrix, and this CPCZ here, our concern, this is pseudo circulant matrix. So first see the similarity between them. If you ignore the Z inverse terms, you can see all of the rows or columns consist of same elements only. If you ignore the Z inverse completely, as if they don't exist, they all consist of C naught Z up to Cn minus 1 Z. So this part matches with the circulant structure. Only thing that makes it pseudo circulant is the introduction of Z minus Z inverse term here. Because once you include Z inverse term, you can see the definition of circulant matrix, that each row have same elements. But for this matrix, if you consider this row, first row, last row and first row, you can see here Cn minus 1 is multiplied with Z inverse, where Cn minus 1 is multiplied with no exponential of Z. So therefore essentially these two are different elements, so the circulant property is being violated here. So although it has shared the similar structure to circulant matrix, it is not a circulant one, it's a pseudo circulant. So let us investigate the Toeplitz property of it. Before saying what Toeplitz property represents, we see that for this matrix, across the diagonals, can you see that across the diagonals their elements are same, like this? Sorry for the drawing anyway, because this is a dull structure I have drawn, but yeah, just a moment. Okay, let me try to highlight in a good manner at least. Okay, you see across these diagonals the elements are same only, C not Z. Not only that, if you see across this diagonal Z inverse Cn minus 1 Z, here also Z inverse Cn minus 1 Z to this, across this diagonal also they are same, and also this diagonal C1Z, 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 these across these diagonals the elements are going to be same. However, if you see diagonals in this direction, let me change the color of highlighter here. Yeah, this one maybe across this diagonal, or if we write the element here, let me write it here, uh, C2 of Z here. You see across this diagonal, are those elements same? See, here it is C1 of Z, here Z inverse Cn minus 1 Z, not same. Similarly this also C2Z, just a minute. Yeah, it's fine. C2Z, C naught of Z, Z inverse Cn minus 2Z. So across this diagonal, so let me write it down. We see across yellow highlighted diagonals, all elements are same. Whereas across blue highlighted diagonals, elements are different. If you carefully notice what is the difference between yellow highlighted and blue highlighted diagonals, you'll see yellow highlighted diagonals are descending diagonals. Descending. If you observe from left to right of the matrix, they are descending diagonals. This one consisting of C naught of Z is the principal diagonal, of course, and these diagonals across which all elements are different, the blue highlighted one, if you observe from left to right, are nothing but ascending diagonals. Ascending diagonals. So this observation sums up the Toeplitz property. We'll give the definition, but I just want you to know what's exactly happening, so that even if you don't know the technical definition of Toeplitz property or Toeplitz matrix exactly, you can sum up what's exactly happening, the crisp of that, from this observation only. So according to the definition, Toeplitz matrix is a matrix in which each elements across every descending diagonals from left to right are same. Another way of saying that each descending diagonal from left to right are constant. And this is the Toeplitz property. Now this CPCZ, which is a pseudo-circulant matrix, satisfies this Toeplitz property. Therefore, the Toeplitz, it's a Toeplitz matrix. Let me write it down. It's a n cross n. Therefore, it's a CPCZ is a Toeplitz matrix. It's noteworthy to mention that if you see the circulant matrix here, does the circulant matrix satisfies the Toeplitz property? You can say it does actually. And the pseudo-circulant matrix also satisfies Toeplitz property. So let us write down these observations. Both circulant and pseudo circulant matrix satisfies Toeplitz property. So Toeplitz property is more general because Toeplitz property is more general. And why is that? As all circulant matrices or circulant matrices are Toeplitz matrix, but not vice versa. So every circulant matrix are Toeplitz matrix, but not every Toeplitz matrix is going to be circulant. An example is the matrix in our problem CPCZ. It's pseudo-circulant, but it's Toeplitz also. So therefore, if we denote this as Toeplitz, this is scope of Toeplitz matrices, whereas circulant is a part of it, a subset of it. The scope of Toeplitz matrices are bigger. So let's come back to our question here. It says that, so therefore property of matrix is not circulant, it's pseudo-circulant, it's Toeplitz, and it's not symmetric anyway. Why not symmetric? Just let me write down here. CPCZ is not symmetric from the definition of symmetric matrices, which is because, let me write down here, you can just check the elements here, you can understand yourself that CPC of Z not equal to CPC Z transpose. If you basically transpose means your columns becoming row and rows becoming column. So if you consider the first row and first column, if they are not interchangeable, therefore your matrix is not going to be symmetric. You can clearly see for the first column consists of no Z term, whereas the first row except the first entry, all the elements, all the entries of the first row have Z inverse term. So clearly first row and first column are not interchangeable or identical. So therefore this CPC, this pseudo-circulant matrix, is not a symmetric matrix. So therefore first and third are both wrong, only satisfy the Toeplitz property. So this one is the correct answer. With that, let us move to our third question. So here we are asked that the matrix formed by this channel polynomial in Z, Cz is given by this expression 2 plus 2z inverse 3z minus 2, 4z to the power minus 3 and 5z to the power minus 4. You can see there are 5 coefficients, therefore number of channel taps are 5. So this channel forms this matrix which we have considered in the just previous problem, which is of size 512 cross 512. So what is the sum of eigenvalues of matrix? So the brute force way of computing eigenvalues, which we generally take by if you remember this formula you all used from linear algebra, that determinant of a minus lambda I and solving equations and finding the value of lambda, although that holds for a matrix whose dimension are small, it is definitely not feasible for a 512 cross 512 square matrix. So you cannot compute eigenvalue of this matrix in a direct manner. You need to have some other properties, some algebraic properties if used. So if you remembered this pretty much well-known linear algebra property that sum of the eigenvalues is nothing but equal to trace of the matrix itself. Therefore, if you know the elements of the matrix along principal diagonals, even if you need not know them separately, if you know the sum of the elements across principal diagonals, that is equal to your sum of eigenvalues. So that's it. All you need trace of this matrix. To be more specific, you need to know the sum of the elements across principal diagonal. So let us see. Although we have a hint from previous question that when you say sum of the elements across principal diagonals, you see principal diagonals consist of these elements C naught, only C naughts. So you just since the all the elements of principal diagonals are identical, you just pick number of elements and multiply the value of elements and you'll get. So let us move step by step what's exactly happening. So as given in the question, size of CPCZ is equal to 512 times 512, and it is formed by this channel transfer function CZ is equal to 2 plus 2Z inverse plus 3Z to the power minus 2 plus 4Z to the power minus 3 plus 5Z to the power minus 4. You can write this as C naught plus C1 Z inverse C eyes are channel taps plus C2 Z to the power minus 2 plus C3 Z to the power minus 3 plus C4 Z to the power minus 4. So you obtain C naught is equal to 2, C1 is equal to 3, sorry, C1 is equal to 2 also, C1 is equal to 2 also, C2 is equal to 3, C3 is equal to 4, C4 is equal to 5. Okay. If we follow the notation from the lectures, where it's a number of channel taps are given as mu plus 1, which is 5. Mu is the symbols of ISI or zero padding length or cyclic prefix length. The psi is going to be 4, and the m value we are going to have n minus psi is 512 minus 4 is equal to 508. Since you have only 5 channel taps, therefore your matrix CPC of Z, which is supposed to be a it's a 512 cross 512 matrix, most of these elements are going to be non-zero because you have 512 elements in the first column, but only 5 of them are non-zero na. C0, C1, C2, C3, C4. Beyond that, all are non-zero elements. Sorry, all are zeros. Correct? Because rest of the tabs are zero only. The next column, we know from the property, just your C not comes here. Here comes C1, here comes C2, here comes C3, here comes C4. Let me draw a line here. Which corresponds to when C naught reaches here. C naught, C1, C2, C3, C4. And it's good way to visualize in this manner that all this C naught, they are across these diagonals, these C1s across these diagonals. Similarly for C2, C3 and C4, I am not exactly drawing them. What I am going to do is that here C0 shifted here, C1, C2, C3, next C0 is here, C1, C2 here, next C0 is here, C1, and at the end it's C0 only. If we see here what's exactly going to be happening from here onwards, you will have C4 here, Z inverse C4, and you have Z inverse C3 here, Z inverse C2, Z inverse C1. Things are becoming a little messy here, but I hope you understand what's exactly happening. So if you consider the last column, it's Z inverse C2, Z inverse C3, Z inverse C4. You can draw a mark here also. You see there are only 4 rows. And rest of the here you have 508 rows. Similarly here also including this one, of course, this line including, you have 508 columns, 508 columns. You have this 4 columns. The elements here are going to be 0. Here it's a big 0, here it's a 0, so 0. So although it's a 512 cross 512 matrix, only a very few elements are non-zero here. And we are going to use the algebraic property that sum of eigen values of C, P, C, Z is equal to sum of elements across principal diagonal of C, P, C, Z, which is a mathematical way of saying trace of C, P, C, Z. Now we have already seen from previous question also, and here it is becoming more evident that across the principal diagonals you see the elements are C not only. Therefore the sum of them is going to be trace of, sorry, I won't say trace here, just mention here sum of C naught plus C naught plus dot 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 C naught, and this summation is happening n times, so therefore it becomes n times C naught. Your n value is 512, which is the size of the matrix square pseudo-circulant matrix CPCZ, and C naught we have seen the channel tap corresponds to no delay here. C naught value is 2 here, the constant in the expression Z transform, the channel transfer expression, the constant term corresponds to C naught, which is 2. Therefore your answer is 1024. Therefore using this algebraic property and the structure of this pseudo-circulant square matrix, you can, anyway it's pseudo-circulant, it's got to be square, so square is like mentioning square is being redundant here. So using this particular structure of CPC and the algebraic property, we can derive, or we can find, if we have some objective question to answer the sum of the eigenvalues of this matrix in few seconds only, which comes out to be 1024. You just need to take the size of the channel CPCZ, sorry, you need to take the size of the matrix CPCZ, and you just need to have the channel tap C naught from the channel transfer function, and you just multiply them, you will get the sum of the eigenvalues of this matrix. So the third answer is the correct one. With this, let us move to our fourth question. Fourth question says that xn is a sequence which have 1 2 3 4 5 elements, and hn is also another sequence 7 8 9 which have 3 elements, and the number highlighted in red indicates the sample value at time index 0. So this corresponds to just arrow notation that indicates the 0th index sample, and we are asked to consider two new sequence yn and zn, where yn is the linear convolution of xn and hn, and zn is the 5-point circular convolution of xn and hn. Now the question says, if zn has k non-zero samples per period and yn has l non-zero samples, then what is the value of l minus k? Now this answer can be pretty much straightforward also. We know that circular convolution, first of all we look at linear convolution. Now if I linearly convolve to sequence, discrete time sequence of length n1 and n2. Therefore, the convolved sequence or the output will have length of n1 plus n2 minus 1. That's pretty much known to us from the basic digital signal processing course. Whereas circular convolution is a little more tricky. First of all, how the you must specify the points of circular convolution, that is the length of circular convolution. If you are considering 5-point circular convolution, the sequence, the input sequence you are going to circularly convolve should be of same length. Linear convolution, this is not at all necessary. The input sequences can very well of being asymmetric length or symmetric length. It doesn't matter for linear convolution, but for circular convolution it is mandatory that your input sequences should have same length. So we can see in the problem given here, xn and hn have asymmetric length, that is their lengths are not equal. But to perform circular convolution, it's mandatory to have the input sequences being of equal length. So what you need to do, that is also pretty much discussed in the lecture. You have to introduce redundancy in form of zero padding, that is you need to add necessary number of zeros to the sequence which is of lesser length and perform the circular convolution. So let us move with that. First let us write the sequence xn here. Xn is equal to 1 2 3 4 5. Arrow indicates the 0th indexed sample, and hn is equal to 7 8 9. Okay, now we have linear convolution, and we have here 5-point we have here 5-point circular convolution. Okay, the linear convolution is represented by y of n, that we obtain by linearly convolving xn with hn. Whereas circular convolution we are represented by zn, we obtain by convolving xn in a circular manner. Now notice the difference between the notation hn. Let us mention the length also here. Length of xn is 5. Length of hn is 3. Therefore in let us write down here only below circular convolution, it will become easier to follow. order to perform circular convolution Hn need to be of same length as xn, which can be achieved by padding Hn with 5 minus 3 is equal to 2 zeros. So effectively Zn is going to be circular convolution between Hn, H dash n, where H dash n is nothing but 7, 8, 9, 0, 0. And 5-point circular convolution results into length of Zn b k is equal to 5, which is also equal to number of non-zero samples of Zn. However, for linear convolution, things are pretty much simple. We can use this property, number of non-zero samples in yn is equal to length of xn plus length of hn. Therefore length of xn, we have seen that it's 5, minus 1, by the way, here length of hn is 3 minus 1, so this is 7. Therefore length this is equal to L as given in the question. Therefore Zn yn has 5 non-zero samples per period, where yn has 7 non-zero samples. So we get L minus k is equal to 7 minus 5 is equal to 2, the fourth one here. Okay, here we are given two signals, gn length 3 and elements being 2, 1 and minus 3, and hn where elements are minus 2, 4, 2, minus 1 of length 4. As it's convenient, the numbers in red refers to sample value at time index 0. We are asked to find the circular convolution of gn and hn. So we can do that by this matrix method. That's a easy and convenient way to uh, find the circular convolution, particularly efficient when the size of the sequences are small, which is in this case. So let us write down the gn and hn expressions here. Gn is 2, 1, minus 3. Hn is given as minus 2, 4, 2, minus 1. Now consider we denote the circular convolution. Circular convolution, that is denoted by like this: gn circularly convolved with hn we name the output as Fn. So we have to find the Fn. By the way, you just remember circular convolution property. Once two elements have to be of same length, so whenever one sequence is shorter than other, you have to compensate for that less number of elements by padding suitable number of zeros, so that two sequence become of same length. So in that case, you see your hn has length 4 and gn has length 3. So g is the shorter one, therefore g needs to be padded with 4 minus 3, that is 1 0, to make both of them of length 4, so that we can proceed to perform the convolution. Let me write it here. Length of g n is 3, which is one element shorter than hn. So g hence the sequence gn must be padded with 1 0 for circular convolution with hn to be valid. So we'll first form the circulant matrix of sequence G or sequence H. You can do it both way, but let us do it for G. So circulant matrix G is formed using elements of G. By the way, let us write down the modified G after padding with 0. Therefore it becomes 2 1 minus 3 0, and hn, let us just repeat it here, minus 2 4 2 minus 1. Therefore g of 0 is 2, g of 1 is 1, g of 2 is minus 3, and g of 4 is 0. We are writing this in the separate manner so that it becomes easy for us to form that circulant matrix capital G from the elements of G, that is these ones. Similarly, H0 is minus 2, H1 is 4, H2 is 2, and H3 is minus 1. By the way, this should be not G4, G3. Okay, so what is the structure of circulant matrix of G? I think you can already guess if you have seen the previous problems we have solved. it's going to be like this: G0, G1, G2, G3. Just G3 becomes the next column, G3 becomes the first element of the second column, that is G3 comes here. Rest of the element just shift one unit downwards, the sequence being maintained. Here comes G2, comes G3, comes G1, here comes G0, and here comes G. Sorry, made a mistake here. It should be G0 and it should be G1. It should be G0, it should be G1. Then G1 comes here, then comes G2, then comes G3, then comes G0. It's a circular matrix. If you see whether across the row or across the columns, the elements are going to be same only. Any row is a one unit shifted or rotated to right compared to its preceding row. Similarly, one column to next column from left to right, if we see, the elements are just shifted downwards, and the end elements become rotated in a sense that it becomes the first element of the next row, like next column, succeeding column. Rest of the elements just shifted downwards by one unit. So let us put the values here to get the matrix G numeric format. G0 being 2, 1, 2, 1, -3. Just a minute. 2, 1, -3, 0, then 0 comes here, 2, 1, -3, then 3 comes here, 0, 2, 1. Let me write down the -3 in proper manner. Missed it. -3 here, -3 here, and here becomes 1, -3, 0, 2. Okay, this is the structure of matrix G. Now we form the vector H, form vector H from elements of sequence Hn as follows. That is, H is equal to H0, H1, H2, H3. Remember, the order is important. You cannot just put in any order here. It is given as H0 is -2, H1 is 4, H2 is 2, H3 is -1. Now we need to find, now compute GH. which you compute as follows. First write down the g. 2 1 minus 3 0 0 2 1 minus 3 minus 3 0 2 1 1 minus 3 0 2. And we multiply with minus 2 4 2 minus 1. So let us take the dot product of first row and this column. It becomes minus 4 0 minus 6 minus 4 minus 6 becomes minus 10 and become minus 1 minus 11. Then we take product of second row with this column. It becomes minus 2 plus 8, so it becomes 6, and plus 3, so it's become 9. Next it becomes minus 3 minus 2, that becomes 6, plus 4 10 to 14, therefore it is 14. And the next one, it becomes minus 12 plus 2, that is minus 10 minus 2 minus 12. Okay, and here with the vector we obtain, the elements are actually in order. That is, if the convert sequence we denoted as fn the output, therefore this result we got is in this format only: f1 f2 f3. So therefore we obtain fn as this sequence: minus 11 9 14 minus 12. You can also do whatever you circulant matrix you have created. Of course the answer is not matching here. I guess I take one of this sequence to be wrong, that is like answer is like this: fn is correct for this particular choice of this sequence gn and hn. However, I think I did not put the correct option here, or make some error in the input sequence. However, the procedure is same only, like correct only. For this choice of G and H, you are going to get circular convert F in this format, which is, this indicates the 0th index symbol. Important thing to note here, we have formed the circulant matrix G using the elements of sequence G, and we take the product with the vector whose elements are taken from the sequence H. We can just do the opposite, that is, we form the circulant matrix G, circulant matrix H by capital H from the elements of sequence small h, and we can form the vector G from elements of sequence G, and if we take the product of capital H times small g, we are going to get the same output vector fn here. So it's your choice actually. If we have time, I'll show you how doing the other way will result into the same output sequence. Next we proceed to this question, sixth question for the day. Let's say that linear convolution of x1 and x2 need to be found without using the standard formula of discrete time convolution. Okay, the discrete time convolution formula we use for that. Okay, let us write down the sequences first. That is x1 is a sequence of length 3, 1 comma 2 minus 2. This is 0th index symbol of length 3, and x2 n is 2 0 1. This is the 0th indexed symbol of length 3, and we are interested in finding yn, which is a linear convolution of x1n with x2n. But the trick here is we cannot use the standard convolution formula, which is given as yn is equal to summation over x1k times x2n minus k, where k runs from minus infinity to infinity. So this formula we cannot use. So we are not allowed to use the standard formula of discrete time convolution. So what are the choices we have to find the answer of convolution? First thing, you observe that these two sequences are really small dimension, that is only 3 cross 3. Therefore it's you can think, since it's a LTI system, if you have linear convolution of x1 and n2 in frequency domain, it corresponds to multiplication, correct? So instead of performing linear convolution of x1 and x2, we take the z transform of x1 and x2, we go in frequency domain, that is we obtain y of z by just simple multiplication of x1z and x2z, and just since it's a z transform, you just need to look at the coefficients, and that becomes your taps, or the discrete time domain sequence. So it's a very easy way to do. Another way you can do using matrix method, which is also a really cool thing to do. So you can take both these ways to find the linear convolution, even if you are not allowed to use the standard convolution formula. So let us see the easiest one, which is you just take all the things to frequency domain, that linear convolution will then becomes multiplication in frequency domain. You just take simple product and you look at the coefficients, and boom, you have the output sequence from the coefficients only. So we make use of this property. In first method, we make use of this trick, that linear convolution in time domain corresponds to multiplication in frequency domain. That is, you are supposed to get yn without using this convolution formula. How you do that? You just take x1z, the z transform of xn, using this. Just a moment. Now x1n, let me write it down here. Since you have x1n, this x1n represented 1 2 minus 2, you have x1 of, and this is the 0th symbol, the index symbol. x1 of minus 1 is 1, x1 of 0 is 2, x1 of 1 is minus 2. Similarly, x2 of n is 2 0 1, is x2 of minus 2 is 2, x2 of minus 1 is 0, and x1 of x2 of 0 is 1. So here the summation runs from minus 1 to 1, and for z transform of x2n, which is x2 of z, remember this 0th the index become quite important, because that also determines your coefficient of exponent of z. So if you get that wrong, your z transform will come out to be wrong. Therefore your entire linear convolution, you say, or multiplication in z transform, both collapses and they comes out to be wrong basically. So you have to be very careful when doing that. Minus 2 to 0 for x2, because x2 ranges from minus 2 to 0, x2 I, z to the power minus I. So here we have got x1 of minus 1 as 1, z to the power minus 1 is z, plus x1 of 0 2 is 2, x1 of 1 minus 2, z inverse. Whereas for x2 of z, we get x2 of minus 2 as 2, z to the power minus 2 is z square. So you get 2z square, x minus 1 is 0, so therefore that is gone, and x2 of 0 is 1, so it becomes 1. So we got x1z as this expression, x2z as this. So this yn being linear convolution in time domain translate in multiplication in frequency domain. It just become x1z times x2z. We just substitute the expressions here, z plus 2 minus 2z inverse, 2z square plus 1, we get 2z cube plus z plus 4z square plus 2 minus 4z to the power minus 1 minus 2z to the power minus 1. It should not be minus 1 here. The penultimate term, it is 4z. Okay, if we have seen this, the coefficient corresponds to n is equal to minus 3. This corresponds to, okay, let me first arrange them before writing in this manner. It's a 2z cube plus 4z square minus 3z plus 2 minus 2z inverse. Okay. this coefficient corresponds to n is equal to time instant is equal to -3. This one corresponds to n equal to time instant -2. This one corresponds to n is equal to -1. This one is the 0th indexed symbol, and this one corresponds to n is equal to 1. Therefore, from this we obtain yn as follows. We have 2 at -3, 4 at -2, -3 at -1, 2, this corresponds to 0th index symbol, and -2. So this is the expression of y, 2, 4, -3, 2, 2. So you can see the third answer is the correct one. Third answer is the correct option. By the way, we are yet to see the matrix method for doing the same, so let us move to that only. We need to add a slide for that. Second is second method is consist of using matrix way to find linear convolution. For this, let us put x to n like that, and x1 n, x2 n along the, write down the elements of x2 n across the rows and x1 n along the columns. So x2 n consists of 2, 0 and 1. x1 n consists of 1, 2, -2. Just draw the lines here. So you just take the product of particular position where the intersection, where the two element intersect. That is, for this position, which is at intersection of 1 and 2, row corresponds to 1, column corresponds to 2, therefore there is at least 2 here. Similarly, for this 1, 0, 0, so 1, 1, 1. Here 2, 2, 4, 2, 0, 0, 2, 1, 1. Sorry, 2, 1, 2. -2, -4, -2, 0, and -2, -2. Okay. Now what you do, you just I'm just highlighting few things. You consider this one element, you take the sum across these diagonals. First diagonal consists of only one element 2, second diagonal consists of two elements 4 and 0, third diagonal consists of three elements -4, 0 and 1, fourth diagonal consists of two elements 0 and 2, fifth diagonal consists of again one element -2. So this corresponds to element 2, correct, corresponds to summing across the first diagonal, because it has only one element, so sum is trivial, is 2 only. Second one is 4 plus 0 is 4 only. Third one, it's -4 plus 0 plus 1, therefore it's -3. Fourth one, it's 0 plus 2 equal to 0. Fifth one, -2 only. So therefore your convolved sequence yn is going to be yn is going to be 2, 4, -3, 2, -2. Now the question is how to find the zeroth symbol location for this method. For that we need to mention that x10 value is 2 and x2 zeroth index symbol is 1. So for x1n, this is the zeroth index, the start one. For x2, this is the zeroth index. So we are going to find the position where the row corresponds to x10 and column corresponds to x20 meet. So you can see these two meet at this position at 2 here. Let me mark it out. They two intersect here, that is for this element. So this element is where the row and column corresponds to x10 and x20 respectively intersect. So therefore this diagonal, the diagonal that passes through this element, the sum across this diagonal is going to be your y0. So this is position, so this element is not y0, sum across the diagonal that goes through this element is y0. Remember, this 2 is not our concern. The diagonal that goes through this element, the sum across this diagonal is our concern. It just coincidentally this element becomes 0, so it becomes 2, but if it's 1, therefore your y0 is going to be 2 plus 1 3. So we are not concerned about individual element, we are concerned about these diagonals. and the diagonals that passes through this position, sum of the elements across these diagonals is equal to y0. So let me erase the circle around 2 I made, because that might lead to some misconception. So okay, this is fine. So this corresponds to fourth diagonal, which is here. So therefore you can see we obtain the similar result as we have obtained from multiplication in frequency domain. It comes out to be 2 4 minus 3 2 minus 2 only. So your correct one. So next question, the block transceiver with m is equal to 10 and transfer function cz is equal to this. If we are to eliminate the interblock interference using cyclic prefix, what should be the length of cyclic prefix? This is quite similar to the first question, where the interblock interference is eliminated by zero padding. Here it's a cyclic prefix. However, the concept remains same only, because both zero padded system and cyclic prefix based system incorporate same amount of redundancy. So let me write down the expression of Cz here. 1 plus 2z inverse minus z to the power minus 2 plus 0.8 z to the power minus 3. Therefore C0 is equal to 1, C1 is equal to 2, C2 is equal to minus 2, C3 is equal to 0.8. 4 channel taps. Correct. In the lecture notation, we have it's denoted as CZ is denoted as Ci z to the power minus Ni, that is from 0 to mu. So you have total mu plus 1 channel coefficients or taps, what do you say? So this corresponds to mu symbols of ISI. So since zero padding and cyclic prefix introduces same amount of redundancy, the length, we have already seen for zero padding system you need row number of zeros to eliminate interblock interference. The same is for cyclic prefix also. Therefore the length of cyclic prefix is equal to number of channel taps minus 1. We have 4 channel taps here, minus 1, that is 3. So the cyclic prefix should be of length 3 in order to mitigate the interblock interference. Therefore the fourth option is the correct one. So with this I end today's session. We'll next meet on next Tuesday to discuss problems over the content of 11th week. Thank you all.